So like I already said, that hemoglobin is basically responsible for carrying the oxygen in our blood. Now this hemoglobin is, like I already said, it consists of four heme groups, like 1, 2, 3, 4. This 4 heme combined with 4 chains of globin protein, 2 alpha, 2 beta, and this makes up the hemoglobin protein. Now combining with oxygen, it is termed as oxyhemoglobin, and it is a reversible reaction. It can be bound with oxygen or it can release oxygen very quickly. Okay, so next is the transport of O2. So the transport of O2 means basically how much the oxygen partial pressure in blood can determine the oxygen saturation of hemoglobin in percentage, which is that how much oxygen is bound with hemoglobin, that is the saturation percentage of hemoglobin, and it is plotted against oxygen partial pressure, that is the amount of oxygen present in blood. Now this curve can be shifted according to the conditions or several factors present in our body. Now at high concentration of oxygen in the blood, when the oxygen partial pressure is high, it is quite natural that the oxygen saturation of hemoglobin will be also higher. The hemoglobin will tend to bind with oxygen, but oxyhemoglobin cannot be formed when the oxygen partial pressure of oxygen or the oxygen amount in the blood is lower. So as I have already mentioned, so at high oxygen concentration, oxyhemoglobin forms, but at low oxygen concentration, oxyhemoglobin dissociates to form oxygen and hemoglobin. So as I already said, this is a reversible reaction. So when there is low oxygen content, then the oxyhemoglobin dissociates to release oxygen from there, and when it is a high oxygen content in the blood, then hemoglobin starts associating with oxygen and forms oxyhemoglobin. So this balance is basically shown in this oxygen dissociation curve. So this as you can see, that if the curve is right shifted, which means that in low oxygen partial pressure, the hemoglobin percentage of the oxygen saturation will be lower. That means it will be having decreased affinity for O2. And when this curve is left shifted, which means when there will be an increased affinity for O2, that means in lower oxygen partial pressure as well, the saturation of hemoglobin will be higher. So this is the basic concept behind left shift and right shift. This curve also shows that at relatively low oxygen concentrations, like here, there is an uncombined hemoglobin in the blood and little or no oxyhemoglobin. That is in body tissues. So in tissues, when there is low oxygen concentration, the hemoglobin in the blood contains very little oxyhemoglobin. So the oxygen saturation of hemoglobin is also lower when the partial pressure of oxygen is low. And at relatively high, like at this stage, when the oxygen concentration is higher, there is little or no uncombined hemoglobin in the blood at all. Therefore, all of the hemoglobin, almost 100% of hemoglobin is saturated with oxygen, like we find in the lungs. So therefore it has reached a saturation point and there is no further oxyhemoglobin forming. So at this point, when there is high oxygen partial pressure in the blood, the oxygen saturation of hemoglobin will be 100%. Okay. Now, what is P50? P50 is basically that oxygen pressure, partial pressure, when the hemoglobin is 50% saturated. So at 50% point, when it is almost coming around 26-27 mmHg, and this count is known as the P50 of oxyhemoglobin. So it is a measure of oxygen binding affinity of hemoglobin. So 50% of hemoglobin will be saturated with oxygen when the partial pressure of oxygen is just around 26-27 mmHg. Now, in case of fetal hemoglobin, the curve is left shifted a bit because it has increased affinity for oxygen. And in case of adult hemoglobin, the curve is a bit right shifted than the fetal hemoglobin. This is because the fetal hemoglobin needs to be very much active, as the fetus has to perform a lot of functions. So therefore the hemoglobin is adapted in that way so that it has increased affinity for oxygen. So as you can see, there are several factors which denotes the affinity for oxygen, how it will be left shifted or right shifted, and how the curve will change based upon these factors. So certain factors are there, like the first of all is the hydrogen ion concentration. So a decrease in the blood pH, it shifts the curve to the right, and an increase in pH shifted so the acidic pH of the blood will increase the will decrease the affinity of the oxygen of hemoglobin for oxygen. Like as you can see, when the hydrogen ion concentration increases and the pH decreases, there will be decreased affinity for oxygen. In the same way here also, when the pH is increasing and hydrogen ion concentration is decreasing, there will be increased affinity for oxygen. So this change in the oxygen association for hemoglobin, affinity for hemoglobin, is known as Bohr effect. And this Bohr effect can be is the main factor which causes this Bohr effect is the carbon dioxide. So the carbon dioxide in the blood, it has major two effects. One is that it affects the pH, as we know that carbon dioxide can form carbonic acid in the blood, and therefore it can bring down the pH to the acidic pH. So a further decrease in pH will cause the curve to be shifted to the right. It will decrease the affinity for oxygen. So O2 affinity therefore increases when the pH increases. Okay, and this is known as the Bohr effect. And also CO2 accumulation causes carbamino compounds to be generated, and these compounds can have the effect of shifting the curve to the right, while the higher levels cause a leftward shift. So when the carbamino compounds increase in the blood, so therefore it will shift the curve towards the right. When the partial pressure of carbon dioxide increases, the oxygen affinity will decrease, and similarly when the partial pressure for carbon dioxide decreases, the oxygen affinity will increase. So with the presence of carbamino compounds, there will be a decrease in the affinity for oxygen. So effects of 2,3-DPG. 2,3-diphosphoglycerate is an organophosphate, and it is created in RBCs during glycolysis. Now this 2,3-DPG is basically a byproduct of glycolysis, and it is like an adaptive mechanism because this production of 2,3-DPG increases in several conditions where the oxygen level is low, such as hypoxemia, anemia, etc. And this high levels of 2,3-DPG will shift the curve to the right. That means it will decrease the O2 affinity of hemoglobin, and the low levels of 2,3-DPG will cause a leftward shift here. So in low level, when the oxygen level is low, like in hypoxemia, this 2,3-DPG increases. With this, when it is increasing, therefore the decreased affinity for oxygen is very much evident, and when it decreases, the increased affinity for oxygen will again be restored. The temperature. This temperature does not have as significant an effect as the other factors, but of course the temperature also plays a role. This will a hyperthermia or an increase in temperature will cause a rightward shift. Like when temperature increases, the curve is shifted to the right, and when it is decreasing, it is shifted towards the left. So carbon monoxide is also binds with hemoglobin, and it forms carboxyhemoglobin. This affinity for carbon monoxide is much higher than that of oxygen, and therefore this presence of carbon monoxide will automatically the hemoglobin will obviously have a tendency of binding with carbon monoxide rather than oxygen. So in addition to lowering the potential of hemoglobin to bind to oxygen, carbon monoxide also has the effect of shifting the curve to the left. And with an increased level of CO, a person can suffer from severe hypoxemia while maintaining a normal oxygen partial pressure. So even if the partial pressure of oxygen in the blood is normal, if the CO level is highly increased, then the person can suffer from hypoxemia because it shifts the curve towards the left. So the oxygen affinity will increase, but the hemoglobin has a tendency to bind with carbon monoxide. So in spite of the oxygen being there, it will not bind with oxygen, but it will keep binding with carbon monoxide. Therefore, it will cause a person's hypoxemia. And fetal hemoglobin, like I already mentioned, that fetal arterial oxygen pressures are quite low. Therefore, the leftward shift or the increased affinity of hemoglobin for oxygen will enhance the uptake of oxygen in the fetus. It will facilitate its facilitate its normal activities. So the fetal dissociation curve is shifted to the left relative to the normal adult curve. Now let's come to transport of CO2. So like I already mentioned that CO2 can also bind with hemoglobin and can form carbaminohemoglobin. Now this carbaminohemoglobin, some CO2 is also carried in the blood, and this will help in the release of oxygen from hemoglobin. This is known as the Bode effect. Since in the presence of carbonic anhydrase enzyme, the CO2 that is present in the blood, it will react with the water in the erythrocytes and it will form carbonic acid. Like I already mentioned that this carbonic acid is responsible for decreasing the pH of the blood. And this carbonic acid dissociates to form hydrogen ion. So hydrogen ion increases means pH will decrease. And in acidic pH, I have already mentioned that the curve, oxygen dissociation curve, will be shifted to the right. That means the affinity for oxygen will decrease. So this is also a reversible reaction, and this carbonic acid will also in turn dissociate into H plus and HCO3 minus. So this exists in a dynamic equilibrium, and it will be like associating and dissociating back and forth. So inside the erythrocytes, there are thus negatively charged bicarbonate ions, and these ions diffuse from the cytoplasm to the plasma. Now this is balanced by the chloride ions, since in the opposite direction, maintaining the balance of negative and positive ions on either side. This is called the chloride shift. So here, as you can see, when the carbon dioxide in plasma is diffusing into the RBCs, then in presence of carbonic anhydrase, this is present only in the RBCs. This reaction occurs and carbonic acid is formed. This again is reversible reaction, and it can form H plus plus HCO3 minus. This bicarbonate ions, if it diffuses into the plasma again, then there will be a negative shift here, and this negative potential is balanced by the influx of chloride ions into the RBCs. This process or mechanism of balancing the negative ions is known as the chloride shift. And again, when this H plus is coming in contact with HbO8, which means oxyhemoglobin, then it will again break down into HHB and 4O2. This oxygen will be brought back in the plasma and it will be carried away. So this is how the hemoglobin is taking up oxygen and releasing carbon dioxide here. So I will come to this later. And this dissociation of H2CO3, like I mentioned, increases the acidity of the blood. Then H plus ions then react with oxyhemoglobin to release the bound oxygen and reduce the acidity of the blood. So like I said here, that the affinity will decrease for O2 in increase of H plus ions or decrease of pH. So that is exactly what will happen here. And this reaction will happen. This is a reversible reaction, and this is completely due to the Bode effect. That is the CO2 increase, the pH decrease, and this increase of H plus ions. This phenomena is known as the Bode effect. So CO2, like we know, is a waste product of respiration, and its concentration is high in the respiring cell. So hemoglobin is now releasing oxygen here, and now Hb is strongly attracted to CO2 molecules. So CO2 is removed to reduce its concentration in the respiring cells. and therefore it is transported back to the lungs, where the concentration of CO2 is lower and the concentration of oxygen is always high in the lungs. So therefore the opposite process will happen in that, and from there oxygen will be again uptaken and it will be brought back to the tissues. So this chloride shift phenomena is also known as the hamburger phenomena, named after this hot dog hamburger, and it is a process, like I said, it is the exchange of bicarbonate and chloride ions between the plasma of the blood and the RBCs of the blood. So this is known as chloride shift, and it mainly happens because of the carbonic anhydrase enzyme, which is present in the RBCs. It spontaneously forms carbonic acid by reaction with the carbon dioxide and the water present in the RBCs, and therefore with this carbonic acid, when it starts dissociating, this process is helpful because this creates a lot of bicarbonate ions inside the RBCs. This bicarbonate ions, when it goes outside the RBC, the chloride comes in and it balances the negative charge in the RBC. So this exchanger, anion exchanger protein, is known as band 3, which is present in the membrane of the RBCs, and via this band 3 protein, exchanger protein, this chloride and bicarbonate ions are exchanged between the plasma and the RBCs. Thus, the rise in intracellular bicarbonate leads to bicarbonate export and chloride intake. This term is known as chloride shift. Okay. So this is shown here. So the Haldane effect. The Haldane effect is basically just the reverse of the chloride shift, and that is when the PO2 rises and PCO2 falls, that is in the pulmonary capillaries of the lungs. Of course, the oxygen pressure is much higher than the carbon dioxide pressure. Then the Haldane effect occurs, which means the release of carbon dioxide from the hemoglobin during oxygenation of the blood. So this releases hydrogen ions from hemoglobin, increasing the free H+ concentration within the RBCs, like this. So within the RBCs, this H+ concentration is increasing, like here, and therefore this H+ concentration is shifting the equilibrium towards CO2 and water formation from bicarbonate ions. So what happens is that there is a decrease in intracellular bicarbonate ion concentration, and it reverses the chloride bicarbonate exchange. So bicarbonate moves into the cell and chloride moves out from the RBCs. So this is the reverse chloride shift, and an inward movement of bicarbonate via the band 3 exchanger allows the carbonic anhydrase enzyme to convert it into CO2 for expiration. So this CO2 is again converted back. So as you can understand that this Haldane effect is just the opposite of the chloride shift. What happens is that in the pulmonary capillaries of the lungs, this thing happens. When the oxygen pressure is quite high, then the hemoglobin will tend to form oxyhemoglobin and it will tend to release carbon dioxide. So when it is releasing carbon dioxide, then the HHB, that is the reduced when the hydrogen ion combined with hemoglobin, that is releasing H+ ions. This H+ ions will go and it will form, it will start acting with bicarbonate ions, and it will form the water and CO2. So this is a fast process, and this water and CO2, this CO2 will be expelled out into the alveolus. So in the alveolus, as you can see that the O2 is coming into the RBCs of the present inside the capillaries, and the CO2 from the RBC of the capillaries, it will be passed on to the alveolus. So just the reverse process will take place. And some CO2 is also dissolved in plasma, that will also be released, and some O2 will come inside the plasma, diffuse into the plasma, and it will dissolve in plasma as well. So this process, this is a slow process where CO2 and H2O is forming H2CO3 and all that, but this process is faster. This carbonic anhydrase from the bicarbonate ions, this is a faster process which is happening in the RBCs. So this is allowing a reverse chloride shift because the bicarbonate ions are getting used up inside the RBCs. So it will come inside the RBCs, and the chloride from inside will be expelled out from the RBCs, thus maintaining the negative balance. So the oxygen dissociation curve will obviously shift to the right in case of Bohr effect, where there is oxygen affinity will decrease, and this Haldane effect is obviously increasing the oxygen affinity of hemoglobin, so the curve will shift towards the left. So the pH is increases since H plus ions are used up, so pH will increase, the DPG will decrease, and the temperature will also decrease, and therefore it will be shifted towards the left. Just the reverse cases will happen over here, and therefore in Bohr effect, thus curve will be shifted towards the right. So this entire mechanism is how the O2-CO2 transport is happening, how the gases are exchanged in the lungs as well as in the tissues, and so this chloride shift and Haldane effect are both very important for maintaining this fast dynamic equilibrium inside the body. So that is all for respiration.